Welcome again to electrostatic fields. Finally, we are with our ultimate goal, calculation of the capacitance and what's called boundary valued problems. Capacitance is nothing but a ratio between the charge Q and the voltage V. And we have learned that based on what we are given, either we are given rho L or rho S or rho V or the Q itself. This is the total charge. This is charge per unit length, charge over surface, and charge over volume. And based on this one, we can make the triple integral to get the total charge, double integral to get the charge, or single integral to get the charge again. We are more interested this time in surface charge because our assumption here we have two conductive plates. Between them is dielectric, which will form what's called the capacitance. Since we have conductors, we have learned in the previous video that electric field is related to the charge over a surface, like based on this one. E equal to rho s over epsilon, and its direction is normal to this conductive surface. So we can rewrite rho s equal to epsilon E dot n. If we substitute in this equation here, this equation will reduce to this form, double integral over the surface of epsilon E dot n ds over the voltage, which is nothing but minus integration of the from the negative charged conductor to the positive charged conductor E dot dl. So here we are being asked to calculate the capacitance of parallel plate capacitor, which is nothing but two flat surfaces charged with opposite charges. Here we have uniform charge density, positive rho s and negative rho s, and this direction is the z direction, or we can call it k. To calculate the capacitance, we just need to calculate q, calculate v, divide them by each other, then we can get the capacitance. To calculate the charge itself, it is very simple. Since we have the surface charge, we substitute double integration rho s ds. We need to know what is ds. We have the perpendicular here is z, then the surface will be in xy plane, so we can substitute ds by dx dy. Then our charge is nothing but rho s, and it's uniform. We place here, since it's uniform, we can take it outside from the integration. We are left with 1 here. If we complete this integration, and since we are not given the dimensions, so we just say this is just the area, because if we look from above here, we'll find the surface here. This is x and this is y. Then if we assume this surface here is just x, y is, we name it area. So we got now q. Then we move to the calculation of uh, v. To calculate v, we need e. And since this is a conductor, we know that e will be perpendicular to the conductor, and it is related to rho s by this equation. So E equal to rho s over epsilon in the normal direction. And our normal direction here, since we assume this direction is k, then our normal is just k. Substitute by this equation in this integration, we got to move here. So we start from d here, and we go to 0, this one, 0 and d. And then we substitute with the electric field from this equation, rho s over epsilon in the direction of k, multiplied by the perpendicular to this surface, which is k, dz. K multiplied by k is 1. Then we are left with rho s over epsilon, and both of them are constants, so we can put outside the integration. And don't forget the negative sign here. Then integrate from d to 0. And actually, this part can be rewritten as rho s over epsilon integration 0d dz, because we have the negative sign outside. We can use it to make opposite direction of integration. Finally, once we do so, if you complete this integration, you will get rho s over epsilon z from 0 to d. Then substitute this one, then you will get d here. Now we have v and we have a q. Then we substitute in the capacitance rho s a in the numerator and rho s d over epsilon in the denominator. Just reformulate, then finally you can get that the capacitance of parallel plate is nothing but epsilon a over d. And the important note here is that this capacitance doesn't depend on the charge. Now we move to another topic which we will use to calculate the capacitance in a more systematic way. So this is called a Poisson equation, and let's derive it together, starting from the first Maxwell equation which we have learned earlier, which is divergence E is equal to rho V over epsilon. This was from Gauss's law for electricity. Also know that the potential gradient E equal to minus gradient of V. So we can substitute this equation here. So you can get div grade V, and don't forget minus here, equal to rho V over epsilon. So if you divide both sides by -1, then you can rewrite div grade V equal to minus rho V over epsilon. And actually this relation is nothing but what's called nabla square, and this right hand side is the same. And this equation is named the Poisson equation. Lambda squared, this is the Laplacian, and this is specific equation we will not use, but we know use another version of it, which is called Laplace equation. But this Poisson equation is used to calculate the capacitance in semiconductors where the charge is distributed over a volume. But in we are interested more in capacitance, which is in a conductive surface, and between these conductive surfaces there is some dielectric. So now we are with Laplace equation, and Laplace equation is the same as Poisson equation, but we assume here rho v is equal 0, and in that case the right hand side will reduce to 0. This of course doesn't mean that we don't have charges. We do have charges, but like the thing which we have learned, we have two plates, whatever is the shape of these two plates. Between them there is some sort of dielectric, and we have surface charge in these plates, rho s and minus rho s. For your reference, this is how the Laplacian is calculated for any scalar field, say V. So whether you have Cartesian, cylindrical, or spherical coordinates, just use this equation to calculate the Laplacian. So before conclusion, we will see how to use this Laplace equation to calculate the capacitance. Normally, we will be given some structure. We will assume that there is a voltage difference between the two plates, and we will use this knowledge and use also Laplace equation to calculate V distribution in the dielectric. Once we know V, and with reference to the boundary conditions, which we have learned in the previous video, such as that conductor boundary condition is Et equals 0, and the normal of the electric displacement vector D equal to rho s. And also we learned some boundary condition as shown here for dielectric. We will check later this one. So once we use all of this information, we can find the V, or the boundary value solution of V. Once we know V, we will apply the gradient, or the gradient relation between E and V, to calculate the electric field E. Once we do so, now we know E, we can use the relation between E and rho s to calculate rho s. Then from rho s we can calculate the charge, and again we substitute in the equation of C equal to Q over V to calculate the capacitance. Thank you.